Welcome to the second lesson for Thanksgiving week for linear algebra. In this lesson, we will look through how to represent functions as power series. So, for right now, what I want you to consider, okay, here's a quick fun fact that's mixed in. So, scientific calculators did not hit the market until the 1970s. The first company to put out a scientific calculator was Hewlett-Packard. However, they were soon followed by Texas Instruments, who undersold them. In terms of Texas Instruments gave a better price. It is interesting because, of course, now most the calculators that we ask you to use are Texas Instrument calculators. So yes, those date to the late 70s. Now, before the 1970s, for trig functions in a high school or college course, you would either have to use a table or you'd have to use another method. So with that in mind, I'd like you to work through these first two problems. So the first one, I want you to calculate 1 minus 0.8 squared over 2 plus 0.8 to the fourth over 24 minus 0.8 to the sixth over 720. Then, using your modern scientific calculator or an internet analog, calculate cosine of 0.8. And I want you to compare those answers. And I want you to think about which one of those could you have done without a scientific calculator. So without further ado, if you use a scientific calculator to calculate 1 minus 0.8 squared over 2 plus 0.8 to the fourth over 24 minus 0.8 to the sixth over 720, you get 0.696703. By the way, yes, I did round that. However, I rounded it a ways off because, well, you'll find out soon enough. If you plug in cosine of 0.8, making sure you have the calculator in radians, you get 0.696707. Those values are very, very close. And that shows you the type of approximation that just 4 terms can give you. If you remember the other presentation, this is a version, or specifically, this is the power series representation of cosine with a number plugged in this case 0.8. And as a result, it gives us a number, it gives us a result that is within 0.0001% of the actual value. That shows you how accurate power series can get, albeit this is accurate because the number is close to 0. The further away from 0 we get for cosine, the more terms we have to use. However, because 0.8 is right near 0, we don't need to use that many terms to get a very accurate estimate. And with that being said, the power series version, you don't need a scientific calculator for. It wouldn't be easy entering this on a really old-fashioned calculator. However, you could multiply 0.8 repeatedly and then divide by whatever number's on the bottom. So the first one could be done with a calculator prior to 1970. By the way, to get a more advanced calculator in the 1960s, prepare to shell out about $10,000. So your choice. Nice car, because by the way, the 1960s, a Cadillac cost significantly less than $10,000. Your choice. If you were in the 1960s, get a calculator or get a fancy car. Unless you're a complete math nerd, that's an easy decision. Now, I want you to start looking for patterns in the way that a power series of a function is calculated. So here, we have the first 5 terms of the power series for sine of x centered at 0. So the terms are 0 plus 1 times x plus 0 times x squared over 2 plus negative 1 times x cubed over 6 plus 0 times x to the fourth over 24. Now, if you need to, pause the recording, but I would like you to calculate sine of 0, the derivative of sine of 0, the second derivative of sine of 0, the third derivative of sine of 0, and the fourth derivative of sine of 0. And I want you to compare those values to what we have. Calculating those values, we have sine of 0 is 0. First derivative of sine, which is cosine. Cosine of 0 is 1. Second derivative of sine, which is negative sine. Negative sine of 0 is 0. The third derivative, which is negative cosine of 0 is negative 1. And the fourth derivative, which is sine of 0 is 0. Notice those numbers match up directly with x to that power. And as it turns out, that is the case for all power series, with the note of the numbers in the denominator. And so now we move on to actually calculating these power series. So now that we have seen how a function relates to its power series, let's talk about this in general and identify patterns. For simplicity, we're going to do a power series centered at 0, as 0 is a nice number to work with. It makes things simpler, especially as you'll see later on from this. So here we have f of x is equal to some coefficient c0 plus c1x plus c2x squared and going on. We want to find out how these coefficients c0, c1, c2, c3, and on up relate to the function itself. If we plug in 0, f of 0 is equal to c0. The rest just go away. So we can write c0 is equal just to the function at 0. Now, if we take the derivative of the function, we get f prime of x is equal to c1 plus 2c2x plus 3c3x squared plus 4c4x cubed. It does go on, however, again, let's use writing conservation here, and we'll just stop right there because we could go on forever, but I don't think you want to hear me talk forever either. So, if we then plug in 0, well, everything except for c1 goes away. So we then have c1 is equal to f prime of 0. So plugged in the function, plugged in the derivative, we got c0 and c1. Well, let's continue down this track and take a second derivative. The second derivative, f double prime of x is equal to 2c2 plus 3 times 2 c3x plus 4 times 3 c4x squared plus going on. I've intentionally left the multiplication, and you'll see the reason in a little bit. Either way, if we plug in 0, we're left with f double prime of 0 is equal to 2c2. If we then divide by 2, we end up with c2 is 1/2 f double prime of 0. Continuing on, the third derivative, f triple prime of x is equal to 3 times 2 c3 plus 4 times 3 times 2 c4x. Plugging in 0 gives f triple prime of 0 is equal to 3 times 2 c3. If we divide, we then get c3 is equal to 1 over 3 times 2 f triple prime of 0. Pause here and look for a pattern. And by the way, you notice we got 3 times 2, which is really 3 times 2 times 1. What thing that you have come across in sequences and series has the form where it's 3 times 2 times 1? Think about it. Going one step further, the fourth derivative of the function is 4 times 3 times 2 c4 It does go on further, but again, just we've written enough. So again, plugging in 0 and dividing, we get C4 is equal to 1 over 4 times 3 times 2 times 1 f fourth derivative of 0. To eliminate the suspense, 4 times 3 times 2 times 1 is 4 factorial. Now, 0 factorial is 1, so we didn't need to write 1 over 0 factorial for C0 because 1 over 1 is boring. Similarly for C1, 1 factorial is 1, and again, you could write 1 over 1. At the same time, 1 over 1 is not necessary to write. So for those of you that want to write more, do some dominant hand energy conservation and just resist the urge to write more if you don't need to. Anyway, this pattern of 1 over n factorial nth derivative at 0, this is the general rule for power series, and this is how we can calculate a power series for a function. Now, power series were coined, or this method was coined by guys named McLaurin, specifically Colin McLaurin, and Taylor. Now, I'll be honest, I don't remember what Taylor's first name is, so look it up. Anyway, let's continue. So the one we used is the one on the bottom. So specifically, we found the rule from McLaurin series, which is a power series centered at 0. Taylor series are another way. Taylor series just centered at A. And so the only difference in the two is for Taylor series, we can take the derivative at a number of our choosing and then subtract that number from x. Please note that for Taylor series, that is a single number, so we're choosing to center it somewhere other than 0. For McLaurin series, we're just centering at 0, which you notice McLaurin series are less writing. Now, there is an issue with McLaurin series, and that is if you have a function with a discontinuity at 0, one example is y equals 1 over x, you can't do a McLaurin series of it because, sorry, but infinity does not work as a term in a series. It just doesn't. So anyway, let's calculate some of these series and let's move on. Now that we've gone over the rules, let's go ahead and let's calculate Taylor series. By the way, we could calculate McLaurin series, however, those are just a special case of Taylor series where we're centering at 0. Now, to calculate a full Taylor series, first of all, it's an infinite number of terms long, so to do that, technically you'd never finish, and to write it in sigma notation, you have to find a rule, which, that would be more work. So for right now, we're just going to find the first 4 terms. By the way, for most practical applications, you only need a certain number of terms anyway, so finding the first 4 terms or the first 3 terms, that's more like what you would actually do, because to find a full rule, there aren't a whole lot of applications for that. So anyway, the key thing about Taylor series is that we need the value of the function and we need the value of its derivatives. So that means we're going to plug our a value into the function. Then we're also going to take derivatives and plug it in there. So plugging in 4 into 1 over square root of x gives 1/2. Now taking the derivative of 1 over square root of x is taking the derivative of x to the negative 1/2. So negative 1/2 comes out front, subtract 1, x to the negative 3/2. And if we plug in 4 into that, we get negative 1 over 16. Then the second derivative becomes 3/4 x to the negative 5/2. Plugging in 4 into that, 3 over negative 128. And similarly, the third derivative is negative 15 over 8, x to the negative 7/2. And third derivative at 4 is 15 over 1024. Now, we're going to plug that into our formula, where we're going to take each of these and we're going to divide it by we're going to take each of these and divide it by n factorial. Or in other words, n factorial is going to go in the denominator. And then we're going to take x minus 4 raised to the corresponding power, noting that x minus 4 to the 0 power is just 1, and x minus 4 to the first power is just x minus 4. Doing so gives us 1/2 minus 3 over 16 times x minus 4. Should be plus, so let's make a quick alteration on that. So then plus 3 over 128 times 2 factorial times x minus 4 squared. Continuing, noting that I made an error with plus and minus signs that now has been corrected. We have the third derivative evaluated for is negative 15 over 1024. And so that becomes 15 over 1024 times 3 factorial times x minus 4 to the third. And again, it continues. So now simplifying gives what we have here, noting the correction on plus and minus sign. And so this is the first 4 terms of our Taylor series. Now, to give another example, let's go ahead and let's do a trig function. Sine and cosine we've already been over and they're boring. So let's do something less boring. How about cosecant? Although the only issue with cosecant is have fun with the second derivative because we'll cross that bridge when we get there. No, we won't. It's a power rule. So, cosecant is fun. For me, maybe not for you, but oh well. So, again, if we plug pi over 4 into cosecant, we get the square root 2, which is 1.414. Derivative of cosecant is negative cosecant times cotangent, and plugging in, we get negative 1.414. Then, if we take the second derivative, it's a nice product rule. I know your favorite thing, right? And we get cosecant squared times cotangent plus cosecant cubed. And that will result, after a fair amount of calculator work or a fair amount of mental math, whichever you prefer, as 4.828. Putting that all together results in the Taylor series, the first 3 terms of one, that is, 1.414 minus 1.414x minus pi over 4 plus 4.828 over 2, because please note the 2 factorial is 2, times x minus pi over 4 squared. And for our purposes, that's fine. You could go further, but again, for those of you that want more work, feel free to go for it, but not for me. I'm not going to do more work. So now let's move on to some common McLaurin series. Okay, so there are some McLaurin series that you will see somewhere else, almost guaranteed. So here are the 4 that are the most common. So first of all, I put it on there even though it's not incredibly common, but the McLaurin series for 1 over 1 minus x is just the sum from n equals 0 to infinity of x to the n. By the way, this is a geometric series representation. Then the power series, or the McLaurin series, for the good old common exponential, or natural exponential, e to the x, is the sum n equals 0 to infinity x to the n over n factorial. So that nice thing that it's its own derivative, there's its power series. If you want to, you can verify that its power series is its own derivative as well. You can, but you don't need to. And then we've sort of been over it, but cosine x is sum n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And sine of x is n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Now, a key thing about these is they can be customized to some degree, and that means you can replace x with whatever's inside the function. So on the right-hand side of this, we are going to write the McLaurin series for two functions that are similar to those, but not exactly the same, just to demonstrate that yes, you can represent these as power series just using these formulas. We're not going to bother with taking derivatives because, again, we don't need to do more work. For those of you that want to do more work, please remind me when you come back to class so I can put up some sandbags and barbed wire to save me from you. Anyway, back to this. You don't need to do that much work to calculate these. So for example, for e to the 3x minus 2, all we do is we take the series for e to the x, but instead of x, just write 3x minus 2. We now have a power series, and for our purposes, we're done. Yes, you could expand that out. However, again, those of you that want more work, give me a warning when you come into the room. Then, if we sine of pi over 3x minus 7 pi over 4, just take the series for sine and replace x with that. And so we get sum n equals 0 to infinity, negative 1 at the end, times pi over 3x minus 7 pi over 4 to the 2n plus 1 over 2n plus 1 factorial. That's all. Thank you for staying with me on this video. I hope you learned something from it. You are more than welcome to email me with questions. Have a good day.